We're going to take a field trip along the James River in central Virginia, starting here on the west with the Scottsville Triassic Basin. Here's the James River flowing down through central Virginia. And look at the names of some of these counties: Buckingham, Fluvanna, Goochland, Powhatan, Cumberland. But we're going to start over here in the western part of the Piedmont at a place called Totier Creek Reservoir. Well, I like taking people to new places, and this is an interesting place right here in central Virginia that not a lot of people visit. It's the spillway of the Totier Creek Reservoir west of Scottsville, not too far off the beaten path at all. And there's quite a bit of water coming through here today, so it's a little louder than I was hoping, and a lot of the rocks I wanted to look at are covered up with rushing water. But let's see if we can make our way down this sketchy little trail here and find something good to look at. So here on the wall of the spillway, we see this fairly fine-grained, quite fine-grained, flaky rock, kind of like shale, and it breaks off into these little plates like this, and they're kind of shiny, which means that there's a lot of flat minerals in there. But you see how this rock has a distinctly greenish tinge to it, a greenish color. That's from a flaky mineral we call chlorite, and it is in fact a metamorphic mineral. Chlorite is one of the first minerals that forms at green schist facies metamorphism. So this is the first phase of metamorphism when rocks start to heat up. So these are metamorphic rocks, but they're quite low-grade metamorphic rocks, and this is typical of the Western Piedmont of Virginia. And initially I said these rocks are somewhat shaly in appearance, and the fact is they probably started out like a shale started out as some kind of mudstone or some kind of mud, very fine-grained sediment that was initially deposited in fairly deep water. And through time and deep burial, these rocks have been compressed into this quite shaly-looking material that we call phyllite. And phyllite is really the primary rock type in the Western Piedmont. In a metamorphic rock, we call the layering foliation. The foliation, like the folia or the leaves on a tree or the pages of a book, it's the flat layering defined by the alignment of mineral grains. And these flat layers help us understand the geology in a number of ways. The first of which is that it helps us understand the structure of the rocks. Have these rocks been folded in any way? The foliation will help us determine that. And if we stand back just a little bit, you can see, in fact, that the foliation in these rocks is contorted here. You can see that right here, it's dipping off to my right, but then in just slightly off in the distance, it tips over to my left and then goes back over to the right again. So these are gentle folds within the foliation, and this tells us that these rocks are deformed. So let's see if we can extract a little more information out of these rocks. I'm going to do what we call taking a strike and dip on this foliation surface, and this gives me the compass orientation of an imaginary horizontal line drawn on this surface, and I've got my spirit level bubble here to tell me when my compass is level. And then I read off of the compass needle that the strike on this is about north 25 east. So remember that, north 25 east, and the dip, the direction in which the layering is inclined. I'm going to come down here and use my other spirit level, the one I've got my finger on the back here, and you can see that little bubble moving back and forth when I get it level. Then I can read the dip off of the inclinometer down here on the bottom. Oh, and the dip's about 25 degrees too. So the strike is about north 25 east, and the dip is 25 degrees off to the southeast. Let's try this in a different spot. Okay, we're going to take another measurement on this foliation here, and I'm really only about 6 feet from where we were before, but this particular horizon here, this particular foliation surface is dipping in a different direction. I can tell that just by looking at it, but we're going to go ahead and take a measurement here, and I'm going to lay the compass against the rock, get a good level on that bubble, and look at that. Over there we had a strike that was northeast. Here we're actually looking at north 80 west. North 80 west is the strike, and the dip is, there's that white arrow on the compass. The dip, the inclination direction, is almost due north, so let's get a measurement of the inclination here. And again, I use the spirit level on the inclinometer, and I get a measurement of 20 degrees. So north 80 west, 20 degrees toward the north. So let's use this surface here as a little chalkboard, and we'll analyze that information we just collected. Let's imagine that, and I'm just going to draw with this pebble here, that this is our north arrow, and that first measurement we took was north 25 east, so that's about like this. So I'm going to draw a strike and dip symbol, which is a straight line like this, and then like this. So that's north 25 east, and we had a 25 degree dip. You're not going to be able to see that. But then our other measurement was about north 85 west, almost perpendicular, more like that, almost perpendicular to the north arrow, with a dip like this, and that was, what was it? It was about 20 degrees toward the north. But what we're seeing here is some of these surfaces are dipping toward the southeast, and some of the surfaces are dipping toward the northwest. And what does that tell us? It tells us we've got folds. It tells us that we've got folds. Here's our northeastern strike and southeastern dip, our northwestern strike and northern dip, really a north-northeast dip. And so we can almost see the shape of the folds here in our mind. And what this tells us is these limbs, that's what we call the sides of the fold. The limbs are the sizes of the fold. The limbs or the sides of the fold. One limb is dipping off to the southeast. The other limb is dipping almost due north. And what that's showing us is that we have folds that plunge off to the east-northeast like this, or the northeast really. So let's see if we can actually observe those in the outcrop. So when we stand back from this outcrop and look at some of these surfaces we measured, we can see that some of them over there, here, right over here, you can see that some of these foliations are dipping southeast like this. Here we are looking more or less northeast. So some of these surfaces are dipping southeast, and some of these surfaces, like this one right here, are dipping more north or northwest. So you can see that in this outcrop, there are actually folds. You can see like this, and like this, and like this, and like this, and like this. And let's take a little closer look at some of these folds. And here you can see that these rocks have these nice kinks in them. Here right in front of us, this surface is dipping toward the northwest. And just a few feet away over here, the rocks are dipping to the southeast. So we have a little fold right here in front of us, and that's an upfold. In geology, that's what we call an anticline. Here, just a little farther east on the outcrop, you can see some of these surfaces are dipping very gently to the southeast. Some are dipping very gently to the northwest. These limbs that fold toward each other, in geology, that's what we call a syncline, a type of fold. From this vantage point here, you can see that there are actually quite a few of these folds in this rock here. We see a little anticline, over here, and then a syncline, and then an anticline, and then here in front of us another beautiful syncline. So these rocks are quite deformed, quite folded. So that's the spillway at Totier Creek Reservoir. It's a beautiful spot with a lot of geology to see, and just a nice place to come and relax and enjoy the day.